We usually have models for students to work with because it helps get a visual on what a lot of these different atoms look like if you were to jump down to be the size of a hydrogen molecule. Since you don't have these to handle, I'm going to show you how they work, and I'm going to suggest that you get 4 pins with different colors. Tear a piece of paper into a square and another one into a triangle. On the edges of a square, just draw some little circles, and on the corners of the triangle, draw some circles. This is how you're going to make your at-home kit. You can also use marshmallows and toothpicks if you have them on hand and if you want to play with those too. Now in the pre-lab video, you already learned how to count valence electrons, and then you learned how to do a Lewis dot structure. So for the first one, it was H, C, and N. So that's 3 atoms. And I'm going to give you some examples. So for example, this is an atom, this is an atom, and this is an atom. So that would be 3 atoms. And this is 4 atoms, 1, 2, 3, 4. So notice we have a bond between all of these atoms. That's what I'm going to have your pins represent, so you can see the shape of what's going on. You can see this one has 5 atoms, 1, 2, 3, 4, 5. So if you have your pins ready, if you have 3 atoms, H, C, N, so the C's in the middle, when you draw the structure, where they touch is going to be where the middle atom is. And then on this end is an atom, and on this end is an atom. So at the end of the pins, you've always got an atom. So you can see that this is linear, and this is linear. This is the only one in the kit that kind of looks like this. You're supposed to not see that there's not an option for any other atoms to go anywhere else. The idea is that atoms want to be the farthest away from each other, and the farthest away you can get from each other is 180 degrees. If you had it here, they're not far away from each other anymore. Now they're close to each other. So the farthest you can get is this 180 degrees. So this is the Lewis dot structure. It's going to lead to the electron geometry. So that's like the simple. And for electron geometry, there's only 6 possible name options. So you have the one. This is the next one. This is trigonal, planar, because look, it's in a plane. Like if you could put a piece of paper through it, it would be sitting straight on a plane. There's nothing else sticking out of it. It's a trigonal planar. There is another trigonal, but it's in the molecular geometry naming. Trigonal in chemistry often means triangle or tri or 3. So you can see how this looks like, you know, a triangle on all the edges of it. So trigonal planar. This guy is tetrahedral. Tetra, most people get confused because they think tetra is 4, so it's 4 atoms, but that's not why it's tetrahedral. It's tetrahedral because it has 4 faces. So I've got a triangle here, and so if I were to connect these guys, I would have a triangle face here. On the back, I have a triangle face, and on this side, I have a triangle face. Get it hooked up here. And where's the other one? It's on the bottom. So tetrahedral, tetrahedrons, it's got 4 faces on it. This is easier to see when I kind of cover it up. So let's just look at the top part about this. Now, if you go with that whole idea of little faces and you put all of these around, you can see that you have a pyramid on the top. So see how it's a pyramid? And the base of the pyramid is a triangle. Some bases of some pyramids are triangles and some are squares. So this is a triangle-based pyramid. So here's our pyramid going up to the top. There's also a pyramid going down to the bottom. Can you see them? Going down to the bottom. So to explain the name, it's trigonal because it's a triangle-based trigonal bipyramid, two pyramids. So a pyramid going up and a pyramid going down. That's why it's called trigonal bipyramidal. Last electron geometry category is this guy. And I know you're going to want to call it a square-based pyramid, but they didn't name it that way. They took these faces and you put a triangle on these faces kind of in the same way we did tetrahedral, and you're going to be able to get 1. There's a section on the back, 2, 3, 4, and then you also counted on the bottom 5 faces, 6 faces, 7 faces, 8 faces. So if you imagine it filled in, it almost looks like a diamond if you make a face on all the corners, but it's called an octahedral shape. That's where you have one central atom and then you have atoms on the outside with this kind of an arrangement.
When there are no lone pairs, the molecular geometry has the same name as the electron geometry. For molecular geometry, the space that would normally be occupied by one atom is instead occupied by a lone pair. They're moving really, really fast. It's a pair of electrons. The electrons are so small compared to the size of the atom that we don't see them on most instrumentation. We just see the atoms and where the bonds are, but they are moving very, very quickly and they're occupying that space. Valence shell electron pair repulsion comes into play at this point.
So this guy is called bent. There's another way to get to bent and we can get to him. Now if you take off one more and you put one more lone pair in there, so here and here, you're just linear again. So again, trigonal planar, take off one, it becomes bent. This angle, by the way, is 120. All these angles are 120. 120, 120, 120. Think of a 360-degree circle and you divide it in thirds, so 120, 120, 120. Bent, linear. And again, it has lone pairs. They're just so tiny. You're not even seeing them moving around in there compared to the size of those atoms. So this is a tetrahedral shape, and these angles are 109.5. If you want to replicate that with pins, you take one at the top, you kind of make this angled down shape, and then you add 2 more at the bottom. And this is the hardest one. It's kind of tricky to hold it in your hand. You want those pins to be as far apart as possible. And that's the tetrahedral shape. When you're looking at that, you can see how it's like not flat, it's 3-dimensional. So it means there's an atom here, an atom here, an atom here, here, and here. That is the tetrahedral shape. So like with the tetrahedral, one of the atoms is replaced with a lone pair, or just in case of an atom, you have a lone pair. Let's take the one off the top. So this is a triangle still, so trigonal, we like to say trigonal. And this is a pyramid. It's not flat, it will sit up. You can stand that on a surface. If we take one more off, and we place it with a lone pair, you see that? So that's another bent line. Bent, I just want to point out there are 2 kinds of bent. I'm going to put this one in front. Can you see the angles? So this angle here is a smaller, this is 109.5, this one's angle is 120.